Hi guys, today I'm going to tell you about how to solve knights and knaves puzzles. So you might be taking a course in logic or informal reasoning or critical thinking or something like that, and part of that course you've got to solve knights and knaves puzzles, or maybe you've just come across these and think, how do I get better at solving those? So basically, I'm going to tell you a really simple way to do it in this video. In fact, I'm going to give you several different ways to solve these puzzles, but I'm going to show you the way that I think is the best, the easiest, and the quickest. Okay, so let's get going with that. We are going to start with what are knights and knaves puzzles. So here's the idea. You go somewhere, it's like an island, where everyone you meet, other than yourself, is either a knight or a knave. Knights always tell the truth, knaves always lie. Okay, so you've got these two kinds of people, the truth tellers and the liars. Your job is to work out which. So you're going to meet a bunch of people, they're going to tell you something, and from all of that information, you have to work out whether those people are knights or knaves. Okay, so this is a logic problem, okay? We're going to use logical techniques to give a unique solution. We're going to do some logic and it's going to tell us that person's a knight, that person's a knave. There's no guesswork involved. It's going to give us a unique answer. And the great thing is you don't need to know much logic to solve this. In fact, if you're a complete beginner to logic, you've never studied any logic before, no problem. I'm going to tell you everything you need to know to be really good at solving these problems, even some pretty tricky ones. Knights and Knaves puzzles, they were first published under that name in Raymond Smolyan's 1978 book. What is the name of this book? It's a book basically going through lots of puzzles and paradoxes in logic. So he came up with the name, but the puzzle itself goes way back. So there was lots of different versions of this published throughout the 20th century. I think the idea basically goes back to Bertrand Russell. It's connected to the liar paradox, so the statement, this sentence isn't true, or somebody saying, I'm lying right now, that's basically something that can't be true. And although that's a paradox, knights and knaves puzzles, they're not paradoxes, they're things we can solve, but they're kind of related in that if we hear somebody telling us that they're lying, well, that's information we can use to solve knights and knaves puzzles. So there is this interesting relationship between the puzzle and the liar paradox. There's lots of variants on this puzzle around. One is called the fork in the road puzzle. So basically you're going down the road and there's a fork. One of the paths leads to something good. The other one leads to certain death. How do you know which? Well, there's two people standing there. One always lies. One always tells the truth. You get to ask one question, and based on what they answer, you have to decide which fork to take. A puzzle like this crops up in The Labyrinth, the David Bowie film. Sarah has to work out which door to go through, and she's talking to these two guards, and she works out a solution to the puzzle. So you might want to have a go yourself. You can watch that clip, pause it before Sarah gives her answer, see if you can work out a question to ask of those guards that's guaranteed to give you the right answer. Okay, then watch the clip all the way through, see if she gives the right answer, see if you can work it out. The comments here are pretty interesting. Now is a great time to hit the like button, subscribe to the channel if you haven't already, and if you're enjoying this content and you want to help me make more, you can buy me a coffee over on Ko-Fi or sign up as a channel supporter. Okay, today we are just going to look at knights and knaves. So let's start with some simple cases and we'll build it up to the difficult ones. I'm going to give you two tools to work with. So here I've got a knights and knaves puzzle generator. It's going to give you lots of different examples. I've got a link to that down in the description. It's going to give us easy, tricky and trickier cases. We are going to work through a bunch of these and you put your solution in here and then you click solve and it will tell you whether you've got it right or not. And if you don't understand what's going on, you can click show reasoning and it will explain what's going on. So that is a great tool for learning and testing your reasoning on this. The other tool we're going to use is a truth table generator. Truth tables are basically a way of solving logic problems. There are a gazillion different truth table generators online. If you don't like this one, basically just Google truth table generator and you will get loads. All of them use a slightly different syntax to type your answers in. So we can use this truth table generator as one method for solving these problems. You can, of course, draw out your own truth tables if you know how to do that. If you don't know what truth tables are or how to do them and you would like to, take a look at this video here. But you don't really need to know that for this video. You can use the online one. I'm also going to show you a different technique which doesn't use truth tables at all, which I think in some ways is better. Now is a great time to hit the like button, subscribe to the channel if you haven't already, and if you're enjoying this content and you want to help me make more, you can buy me a coffee over on Ko-Fi or sign up as a channel supporter. Okay, so let's get to it. So here's a super simple knights and knave case. Robert says, Nancy is a knave and I am a knave. Okay, so Robert is either a knight or a knave. You've got to work out which. So you've got to work out whether Robert is a knight or a knave and whether Nancy is a knight or a knave, just based on this one statement. Nancy is a knight and I am a knave, and the fact that Robert says it. Okay, so how are we going to do this? Basically, there's a really simple technique. We just need to know how to write this down in a way that allows us to solve the problem in a super easy way. I'm going to show you how to do that. So what we're going to do is, for each person in the example, so here, Robert and Nancy, we are going to have a sentence that says, Robert is a knight. Let's just call that R, okay? So R is going to be our sentence, Robert is a knight. And you might think, okay, we're also going to want a sentence that says Robert is a knave. But remember, everyone is either a knight or a knave. So if they're not a knight, then they're a knave. So we don't need a different sentence to say that Robert is a knave. What we can do is say not R, okay? Because R means Robert is a knight. So not R means it's not the case that Robert is a knight. In other words, Robert's a knave. So this sentence is going to be our sentence for saying Robert is a knave. We would typically write that down in logic notation with some kind of squiggly symbol here. Different logicians use different symbols, but it's some kind of line before the letter, okay? That means not R. In other words, Robert isn't a knight. He's a knave. So we're also going to want to write down Nancy is a knave and I, Robert, am a knave. Okay, so if we've got N for Nancy is a knight, these sentences are always going to basically mean whoever is a knight. Then we would write not N for Nancy isn't a knight, that is Nancy is a knave, and I, Robert, am a knave, not a knight. So we're using this symbol for and. Sometimes you see it written down like this, but typing it out on the computer, that one's usually a bit easier. Okay, so this sentence is going to mean Nancy is a knave and Robert is a knave. Okay, that's what Robert says. So it's true if Robert is a knight, because knights always tell the truth. In other words, this sentence has the same truth value as this sentence. If this is true, if Robert's a knight, then this one's true. But if this one isn't true, then Robert's a knave, so he's lying, so this one isn't true. In other words, the two sentences have the same truth value. And I'm just going to write that down with an equals, okay? Some logicians put a two-way arrow in between. That's probably the right way of doing it if you're doing logic homework. That's called the material biconditional. It means that the two sentences on either side have the same truth value. But just for the purposes of doing knights and knaves, I think it's easier to remember with an equals, basically meaning the truth value of this one is the same as the truth value of this one. So what we've got there is our translation of Robert says Nancy is a knave and I am a knave. We've simplified it into just two letters, R and N, plus some logical symbols, not and an equals an identity between them. They have the same truth value, we're saying. Now, this sentence is one that we know is true, okay? We don't know whether what Robert says, Nancy is a knave and I am a knave, we don't know whether that's true or not, but we know that it's true if and only if he's a knight, okay? Which is what this sentence here says. So we know that this sentence is true. This is basically how we are going to solve all of our knights and knaves puzzles. We're going to start off with a statement like this. We are going to rewrite it as a logic sentence or like an algebraic identity like this. We know that that's true, and then we're going to solve it. Now, all of these knights and knaves puzzles, if they are formulated properly, there is only going to be one solution. That means the only way to solve this logically will tell us Robert is a knave or Robert is a knight and Nancy is a knave or Nancy is a knight. There will be a unique solution. So one way to find that solution is to stick it into the truth table generator. Now, to put that into the truth table generator that I'm working with, we need a slightly different syntax. We need to write the equals as a two-way arrow, and the and is a double and like you get in programming languages. So we can just rewrite it like that, put it into our truth table generator, and it gives us this table here. Okay, what is it telling us? On the left here, we have all the different combinations of trues and falses to our two letters. N, Nancy is a knight, and R, Robert is a knight. On the right here, we've got the results for the sentence that we're interested in, okay? Telling us whether it's going to be true or false based on those combinations of trues and falses to the N and the R. But we know that sentence is true. So we look down the right-hand column and there should be just one T. There should just be one line where it's true. Okay, we know that that sentence is true, so this is the line that we're interested in. So it tells us that N, Nancy is a knight, is true, so Nancy is a knight, but R, Robert is a knight, is false. In other words, he's a knave. So our solution to that puzzle is Nancy is a knight, but Robert is a knave. Okay, so we can use the online truth table generator to give us an answer automatically. I think sometimes it's better to work these things out in your head or on paper. Maybe you haven't got access to the online generator like in an exam or whatever. Here's a different way to do it without using a truth table. We're just going to kind of think through this sentence here like it was an equation and find a unique solution. So, suppose that R is true. It's equal to this side, which means that this is true. This is an and. It's saying that both bits are true. So if both bits are true, then this bit is true. What we've seen here is that if R is true, then not R is true. But that can't be right because not R being true means that R on its own is false. So if R is true, then R is false. And that's a contradiction. We can't have that. R can't be true, so it must be false. So we have deduced from this not R. In other words, R is false. We've deduced from it that Robert is a knave. Okay, that means Robert's always lying. So this bit here must be false. But not R is true, and that's part of this false sentence here. So if this part was also true, both bits of it would be true, and then the whole sentence here would be true. But it's not. We know it's false. So because this bit's true, this bit's false. So not N is false, and that means that N is true. Okay, there's our solution. N is true, Nancy is a knight, and not R is true. Robert is a knave. So there you go. We've solved that problem just by thinking it through, kind of like you would solve an algebraic equation in maths without using truth tables. Okay, which way should you do it? Should you do it this way or using a truth table? Well, why not do it both? Doing it both ways means you get to hone your skills, and if you get the same answer doing it each way, that's a good indication that you've got it right. It's good to learn it this way because we're going to look at some examples where doing the truth table, pen and paper, is going to be really inconvenient. It's okay if you've got the online generator, but doing it like this, kind of with the equations, is still super simple. Okay, let's look at a second example. Okay, so this is one of the intermediate difficulty examples I've got from the online generator. So now we're meeting 4 people: Wallace, Joan, Edward, and Eunice. Okay, they're each telling us something. So we're going to have to think a little bit about what each is saying. They're not straightforwardly saying this person's a knight or a knave. So Wallace says Edward is untruthful. Okay, untruthful, that's like lying. The only people who lie are knaves. So basically, Wallace is saying that Edward is a knave. So that is going to be the sentence: Wallace is a knight, having the same value as Edward is a knave. I've written it down like this. Joan says Wallace tells the truth. Well, the only people who tell the truth are knights. So Joan is saying that Wallace is a knight. Or we can write that down like this: the value of Joan is a knight is the same as Wallace is a knight. Edward says Joan is untruthful. Well, that's going to be like our first case. Edward is a knight if and only if Joan is a knave. Okay, knaves are untruthful. So E equals not J. Finally, Eunice says Joan is a knave and I am a knave. So that's very similar to the previous example that we looked at. And it's going to be like this. Eunice has the same value as not J and not U. In the previous example, we just had 1 sentence to deal with. Now we've got 4. So we've still got our 2 methods. We can either stick this into the truth table generator, or we can work it out like with algebraic identities. Let's do the truth table generator one first. The truth table generator needs 1 sentence. So the way that we put these 4 sentences into the truth table generator is we conjoin them into 1 sentence using and. So we're going to say this one is true, and this one is true, and this one is true, and this one is true. We can write that down in 1 sentence in the language that the truth table generator likes, like this. Okay, the first sentence, and the second one, and so on. So notice that I've got brackets, parentheses, round each sentence that I'm putting together with and. If you want to understand why that is, go and have a look at this video here. Basically, don't worry about it too much. It's just so that it is the right sentence to put into the truth table generator. Okay, so if we copy that sentence and we put it into our truth table generator, we get this truth table, okay? There's 4 different letters, so we're going to have 16 lines in our truth table. Yeah, it's getting a bit more complicated, but still there's just 1 line with a T in it, okay? We know that this sentence is true, so this is the line we're interested in. So let's look at what the valuation is here. Edward is a knight is false. In other words, Edward is a knave. Joan, that's true, so Joan is a knight. Eunice, that's false, so Eunice is a knave. And Wallace, that's true, so Wallace is a knight. So there's our solution to that puzzle done with a truth table. Okay, so we're already starting to see here truth tables getting pretty big. So as the number of people that we meet in the puzzle increases, the size of the truth table will increase exponentially. They're going to have 4 or 8 or 16 or 32 or 64 or and so on lines in them. And basically you don't want to be drawing those things out on paper. You're going to make mistakes. It's going to take ages. So this is when the other technique, the kind of algebraic technique, I think is clearly the winner. So let's solve the same puzzle in that style. Okay, so we've got these 4 identities and we need to work out which one to start with first. Well, this line here is very much like in our previous puzzle, okay? If Eunice was a knight, this would be true, but then this would be true and that's a contradiction, so that can't be the case. So that 4th line tells us that Eunice isn't a knight, he's a knave. And because of that, not J must be false. Okay, same reasoning as before. This one's true, but this bit has to be false because this is false. So to make this whole thing false, not J has to be false. So if not J is false, J is true. Okay, so we've got our answer for Eunice and Joan. Note here that Edward has the opposite value to Joan. Okay, if Joan is false, then Edward is true. We've got here Joan is true, so Edward is false. Okay, so Joan is a knight, so Edward is a knave. And from this equation, we know that W has the same value as not E. Okay, so that gives us W. So there you go, same answer as in the truth table. So if we just put them in alphabetical order, we've got not E, J, not U, and W. Go back to our truth table, and we've got an F, a T, an F, a T. Okay, so false, true. That basically means the same as not this one, this is true. Not this one, this is true. So we're getting the same answers either way of doing it, which is good, otherwise we'll have made a mistake somewhere. But you get to choose which method you like. This way of doing it with the identities, it hasn't got that much more complicated to go through, even though we've met more people. I guess the advantage of the truth table way of doing it is once you get the hang of truth tables or you use the online one, you're not going to make mistakes. This way of reasoning it through, you can make mistakes, so you have to be careful here. But practice really helps with this stuff. Okay, now let's look at one of the difficult examples, again generated from the online generator. So in this example, we're meeting 6 different people. Beatrice, Eustace, Kirsten, Oberon, Ira, and Zan. Okay, so this is going to get a little bit more complicated. It's one of the harder examples, but we're going to solve it in exactly the same way. Okay, so we're going to go through and translate each line just like we did before. So that is going to look like this. So if Ira's a knight, then Beatrice is a knight. If Ira is a knight, then Eustace is a knave. If Zan is a knight, then Kirsten is a knave. If Oberon's a knight, then Zan's a knight. Kirsten's a knight, then Oberon is a knave. And if Eustace is a knight, then both Oberon and Eustace are knaves. Okay, method number 1, we write that down all as one sentence. We put parentheses around each one and we put ands between them. That combines it into one sentence. Then we can just copy that and put it into our online truth table generator, paste it in, and our truth table is going to have 64 lines. That's because we've met 6 different people, so our truth table has 2, 4, 8, 16, 32, 64 lines to it. You don't want to be messing around with that on a sheet of paper like in an exam or whatever, but if you've got the online generator, no problem. Again, we know that this sentence is true, and there should be just one line with a T in it. Let's scroll down. There's one with a T. It should be the only one. Yes, it is. Okay. So here is our solution. Okay. This is telling us that, B-E-I-K-O-X are respectively knights, knaves, knights, knaves, knights, and knights. Okay. So that's the solution with the truth table. Let's just see how to do this one without using the truth table generator. And I think here we're really going to see the benefit of doing it using the algebraic identity style. This is a great big solution. It's going to take ages to draw this thing out. Let's just see how well we can do it without that. Okay, again, we've got this kind of sentence here. Okay, if E was true, then not E would be true. So that tells us not E. And from that, we get, well, this is false, this is true, so not O has to be false. If not O is false, then O is true. O has the same value as X, so we've got O true here, so we can say that X is true. K has the opposite value to O, so not O is true if K is true. We've got O being true, so we're going to get not K here. Okay, that's good because not K has the same value as X, and we've got X, so we should get not K. That would be a different way of working out not K. So we could there have gone from X directly to not K. So we've got 4 of our answers. We still need an answer for B and I, but I has the same value as not E. We've got not E here, so we can add I, and B has the same value as I, so we can put B in here. Okay, Let's just put those in alphabetical order. We've got B, E, I, K, O, and X. So running through them in alphabetical order, we've got true, false, true, false, true, true. Go over to our truth table generator just to double check. Where's our true line gone? It's here. True, false, true, false, true, true. So yeah, we got the same answer. There's one more kind of puzzle that I want to show you. So here we're meeting 4 people, Mike, Quinn, Neil, and Pat. And a lot of it is very similar to what we've looked at before. Okay, so Quinn says Mike tells the truth, so Quinn has the same value as Mike. Neil says that Quinn lies, so Neil has the opposite value to Q. Mike is saying Neil is a knave, so M has the same value as not N. But here we're seeing a different kind of statement. Mike is saying Neil is not my type. So type here means a knight or a knave. So Mike is saying that Neil is the opposite kind of person to him, right? So Mike is saying, if I'm a knight, then Neil is a knave. And if I'm a knave, then Neil is a knight. So we can write that down like this. Let me break that down for you. Here we've got N equals M. Neil is a knight, has the same value as Mike is a knight. That's like saying they're the same type, okay? It's not saying which type they are, it's just saying whichever Neil is, Mike is the same kind. They've got the same value. But here we've got a not. I've put the whole thing in brackets and put a not there. So if this means they are the same type, this means they're not the same type. Neil and Mike aren't the same type. And that is what Mike is saying. So we can read this as Mike is saying Neil and Mike don't have the same type. Neil is not my type, says Mike. Same thing here. Neil is saying Pat is not my type, so that's going to get the same kind of translation. Neil is identical to P and N have different values, okay? Not P equals N. Now, you might be thinking, how do I work out any information from this? Because I don't know whether Mike is telling the truth or not. So they might be different types, but that's only if he's a knight, right? If he's a knave, he's lying and they'll be the same type. So how does that give me any information at all? Actually, somebody saying X is not my type is a super useful piece of information in a knight and knaves puzzle. Let me just explain why that is. So let's just copy this here. Mike says Neil is not my type. That turns out to be equivalent to Neil is a knave. Okay, it's a bit puzzling why that is, but that is just a logical consequence. Neil is a knave turns out to be logically equivalent to Mike, or in fact anyone saying Neil is not my type. Okay, to get a grip on that, it might help to look at it in a truth table. So let's rewrite that sentence in a way that can go into our truth table generator. We'll paste it in here. Now, this time we've got 2 lines that are true, okay? We know that this sentence is true, so we look at the 2 different ways it can be true. There's the first line and the third line. Now, in those lines, M might be false, it might be true. So it doesn't tell us anything about M. Might be false, might be true, we don't know. But in both lines, N is false, okay? So when we look at a T here, it's guaranteed that N, Neil is a knight, is false. In other words, this sentence guarantees that Neil is a knave. It's equivalent to this sentence here, Neil is a knave. This is super useful information. So in general, if you're solving a knights and knaves puzzle and somebody Y says X is my type, that just gives you for free the information X. You can just write down X is true, it's guaranteed to be true just from that. It doesn't matter whether this Y person is a knight or a knave or whatever. So whenever you see is my type, use that information straight away. It's really, really useful. And similarly, in our case, when we had somebody Y saying X is not my type, that straight away gives us the information that not X, okay? So let's use that idea really quickly to solve this puzzle. We'll write out the 5 statements here, and we know from this line that it's equivalent to not n, and we know from this line that it's equivalent to not p. Not n is the same as m, and q is the same as m. So there's our solution using the algebraic identity method to that, I guess, kind of medium difficulty puzzle. Super quick. We didn't need the truth table. It would have 16 lines, pain to draw it out. We don't need to go that way at all. Really easy to do that once we know this trick here. If somebody says X is my type, that just means X. And if somebody says X is not my type, that just means not X. Okay guys, I hope you found this useful. If you have, do me a favour, give this video a thumbs up, subscribe to the channel if you haven't already. If you've got any questions about this content, leave me a comment down below. If you want to help me out, you can buy me a coffee over on Ko-Fi or sign up as a supporter. Thanks to all the people who've already done that on Ko-Fi. That really helps me to produce more content for this channel. Thanks for watching this far. I really appreciate it, and I hope to see you back on Attic Philosophy soon.